Hello everyone and welcome to my lecture on resonance part 11, where we are going to discuss again why acetyl chloride is more reactive than other acid derivatives. This lecture is in continuation with lecture 1 on acetyl chloride. First, let us quickly recapitulate what we have discussed in lecture 1. Acid derivatives are compounds derived from carboxylic acids. Some examples are acid chloride, ester, acid anhydride, amide, etc. Since the carbonyl group of the acid derivatives is made up of atoms of different electronegativity, the bond is polar and more reactive. Hence, acetyl chloride undergo ready hydrolysis, but ethyl chloride do not. The carbon of the carbonyl group carries partial positive charge and the oxygen carries partial negative charge, as oxygen is more electronegative than carbon. In nucleophilic substitution reaction, more positive the carbonyl carbon, faster is the attack by the nucleophile, and this is the electronic factor. Acyl nucleophilic substitution reaction on acid derivatives are mostly catalyzed by acids, as acids increases the electrophilicity of the carbonyl carbon and the reaction occurs faster. As the nucleophile attacks the carbonyl carbon and the reaction proceeds farther, the trigonal starting material gets converted to a tetrahedral intermediate, which further gets converted to a trigonal product. Therefore, as the reaction proceeds further, the steric factor comes into picture. Smaller the groups around the central carbon, lesser is the steric crowding and faster is the reaction. This is called the steric factor. Therefore, acyl nucleophilic substitution reaction on acid derivatives depends on two factors, one electronic and the other steric. Now coming to our actual question, why acetyl chlorides are more reactive than other acid derivatives? The reactivity order is acetyl chloride greater than anhydride, greater than ester, greater than amide. As we know, reactivity depends on two factors, electronic and steric. Now let us discuss first electronic factor. Here two types of effects are observed. -I due to the difference of electronegativity of the atoms, and +M effect because of the lone pair electrons on the atom, and not only that, the lone pair is in resonance with the double bond. -I effect increases the positive charge on carbonyl carbon, and +M effect decreases the positive charge on carbonyl carbon. And we know that more the positive charge on the carbonyl carbon, faster is the attack by the nucleophile. Now let's look at the electronic effect present in various acid derivatives. Look at acid chloride. The chloride group adjacent to the carbonyl group can have both -I and +M effect. But in chloride, the -I effect is predominant because of the presence of vacant d orbital, and this increases the electropositivity of the carbonyl carbon and the carbonyl carbon is readily attacked by the nucleophile. Whereas in anhydride, both -I and +M effect is observed, and in anhydride, because of the presence of two carbonyl groups, the lone pair on the oxygen is shared at one point with one carbonyl group, and at the other half it is shared by the other carbonyl group. But in ester, there is constantly two effect operating, -I and +M. +M is supposed to be more stronger than -M effect, and therefore it decreases the electropositivity of the carbonyl carbon, and the reaction is slow. Let's look at the amide molecule. Amides are least reactive. Why? The electronic effect around the amide is similar to ester. But still, why ester is more reactive than amide? Let's see. The difference between amide molecule and our ester molecule is that here the lone pair is present on nitrogen. Nitrogen is less electronegative than oxygen. So, +M effect is more pronounced here. Therefore, amides are least reactive in this series. So, taking into consideration of all this electronic factor, the order of reactivity is acid chloride greater than anhydride, greater than ester, and greater than amide. Coming to the steric factor. If you remember the mechanism of the reaction discussed in lecture 1, as the reaction proceeds, the trigonal starting material goes to tetrahedral intermediate, and that again gets converted to a trigonal product. Therefore, as the reaction proceeds, the group comes closer to each other, leading to steric crowding, which slows down the reaction. Larger the groups, slower is the reaction. If you look at the acid chloride and compare it with other acid derivatives, you will find that in acid chloride, the groups are small and steric crowding is minimum. So, the order of the reactivity is again acid chloride greater than anhydride, greater than ester, and greater than amide. Therefore, we came to the conclusion that acid chlorides are more reactive based on both electronic and steric factor. Hence, acid chlorides can be converted into anhydride, ester, and amide. But anhydrides, ester, and amides cannot be converted into acid chlorides. The more reactive derivatives can be easily converted to less reactive derivatives using the following mechanism, but the reverse is difficult. Remember this, the more reactive derivative can be easily converted into less reactive derivatives, but less reactive derivatives cannot be converted into more reactive derivatives, and therefore acid chlorides can be converted into anhydride ester and amide, but anhydride ester and amides cannot be converted into acid chlorides. These are the mechanism of interconversion of acid derivatives. First, when the nucleophile is neutral, and through this acyl nucleophilic substitution reaction mechanism, acid chloride and ester can be converted to amide using ammonia as nucleophile. And this is only because acid chlorides and ester are more reactive than amide. But amides can not be converted into ester and acid chloride. The second mechanism is when the nucleophile is a negatively charged species. Through this acyl nucleophilic substitution reaction mechanism, acid chloride can be converted into anhydride, ester and amide. Acid chlorides can be converted into anhydride. Ester and amide can be converted into carboxylic acids. That's all for today's lecture. If you like my video, please subscribe, share and comment. Thank you and bye-bye.